Okay, so the next concept in linear algebra that we're going to discuss is that of linear independence. Now, I cannot stress enough how important the concept of linear independence is, because it's going to crop up in many theorems and things like that. So, having a firm understanding of what linear independence and dependence is will really be beneficial in the long run. But before we get there, we need to make some initial definitions and assumptions. So, given a vector space V and a field F, we have discussed what a vector space V and field F mean. They are both spaces of numbers that have different properties under they have the same properties under multiplication and addition. That is, for a field, both of them, for a field, its subconditions of addition and multiplication are gonna have different subconditions. That is, of Kane and Kane D, the one of having commutativity, associativity, having an inverse, and having a null element. And then for multiplication, all those in addition to having the distribution over addition. So given those sets of numbers, we want to define first what a linear combination is. So we define a linear combination to be a combination of vectors a1 up to an in V such that they are all added. So it's not a hard concept to grasp. If you have 1 plus 2 plus 3 plus 4, this is actually a scalar combination, if you think about it. Scalar combination, because these are all scalars. So a linear combination is all a combination, but it's going to be of vectors. So given some vectors a1 up to an, the linear given a set of vectors a1 up to an and some scalars alpha 1 up to alpha n, the linear combination constitutes a combination of these products all summed up. So what I mean by that is the linear combination is going to look like alpha 1 a1 plus up to alpha n an. And whatever this is, we don't care. All we know and all we do care about is that this is a combination under addition. Simply a combination of vectors, scalars being there and all. So that's what a linear combination is, simply an addition of vectors. Now they what I want to next discuss is what's called a trivial combination. Think about a trivial combination. Now you have to pay attention to what a trivial combination is, because it's extremely important in defining what linear independence is. Without a concept of a trivial combination, you're going to understand what linear independence is. So let's take some time to discuss what a trivial combination is first, and then understanding what linear independence is going to be much easier. So I'll explain it like this. Let's say we have a certain equation, a x plus by plus cz equals to 0. Then let's say we have ex plus fy plus gz equals to 0. And then let's take hx plus iy j. I forgot what the following letter was there, but never mind. Let's say we have the system of equations. Now let's take a up to j being in F, and X, Y, and Z being in V. Now our vector space V. And we did discuss this conventionality of a field being, scalars, and then these vectors being part of a vector space. So the way I would introduce a trivial combination is that there may be a numerical solution with certain values for a up to j that are not zero. Keep that in mind, the fact that it's not zero. There may be those solutions, but let's say we want to take the easy way out. The easy way out would just be to have x equal to y equal to z equal to 0. Why is this the easy way out? It's because, remember, according to our definitions of a vector space in a field, we needed an under our condition of addition, we needed under our condition of multiplication, we needed a certain element in that set such that it should give out nothing. So that thing multiplied by a certain element should be nothing, and in our case that is 0. So this is trivial because it's our easy way out. If we let all of these things equal to 0, all this multiplication is going to be 0, and hence the left hand side will be 0. So keeping that in mind, let's move to what okay, so just so you understand what a trivial combination is, it's one where all of the unknowns are going to be 0. Now keep that in mind. It's also another important word, those unknowns, because it will play a part with linear independence, and we're going to extrapolate it from the same system. So what linear independence is now let's consider these as vectors, certain vectors, x, okay, a, b, c, plus another certain vector e, f, g, plus h, i, j. And let's equate this to something. Let's equate this to theta. We discussed this in the last class, that theta is our 0 vector. For some reason in maths we just love equating things to 0. It just makes it's actually just the basis of equation solving, but don't worry about that for now. But what I do want to emphasize is that this is going to be equal to the 0 vector. In our vector addition, we defined vector multiplication to have those scalars. So let's have scalars x, y, and z. Now we can consider, now this is where I'm going to introduce linear independence. Linear independence is where for each linear combination, so I'm going to write this down, for some linear combination, if the scalars give out a trivial answer, that system is said to be linearly independent, else linearly dependent. So the system is linearly independent if we are taking the easy way out, you can say. if all of our unknowns, if all of our scalars are 0, the system is linearly independent. And you'll see this type of idea coming in a lot, and we'll do some examples concerning that. But if all of our scalars with this system of vectors are 0, keeping in mind that there are certain conditions for vector addition and so on, if those scalars are all 0, it means that there doesn't exist another linear combination that gives out a system to become 0 on the right hand side. If such a system does exist, where its scalars, these ones, are 0, then our system is linearly independent. However, coming back to this case, if there does exist a solution to the system of equations, then it is not linearly independent. Why? Because there is some other way for us to get to this column of zeros. Because now, notice that in a linearly dependent system, there are two solutions. The solution that, according to what we have defined, the hard solution. So the solution of normal scalars. Any scalar that would make this system become 0. Then there's the solution of zeros, the lazy solution. One where if we add in zeros there, it would give us the 0 column. So that system is not linearly independent. Why? Because it depends on some other solution, which would more often than not be preferred than the complete lazy 0 solution. So yeah, that is what linear independence is. If you have any comments, just post them in the comment section, and then I could deal with them.